No, I want to do the other one. So I know we did one like this the other day. I put two of them on there, and I just changed this. I would like y'all to do the number 11 one, but it wasn't there when you started. So if you didn't do the one that I'm going to look at here, then don't worry about it. But, so this one with this cat, that's a base off of a shell. What happens to that base is it has potential energy because it's up high, has the potential to fall down. And as it falls, it speeds up in the down direction, so then its energy is converted from potential energy into kinetic energy. This one. There we go. All right. I didn't realize that I put the same concept on 2 days in a row. Anyway, today we're doing a torque problems. We're going to do some calculations with torque. We did our torque lab where we balanced stuff. But first, I would like to start off with a feat of strength. This is a bar and some duct tape and a hammer. I like to call it Torque's hammer, since we're doing torque. Get it? The Avengers thing. Or it's more of like a Nordic mythology thing. Norse mythology. Norse mythology. There, I said it. So like I can totally lift this. Look at this. I can even lift that here and do it. Do I have a volunteer that would like to see if they can do this? Don't worry, you're not going to be on camera as long as you don't come past here. Yeah. Let's try it out. Try it out. I appreciate it. We've only got 8 people in here. I don't know where. Oh, it doesn't matter. It weighs the same, right? It's an 8-pound thing or something. Here you go. Okay. Oh, you can't do it? Wow. Anybody else? Look, I can do it. Obviously, this is a trick. It's when I'm holding right here, all the weight's like way down here, right? So if I hold it right here, I guess my lever arm is from here to here. If I'm holding it way out, or if I'm holding it closer, then it's just from there to there. So if I multiply however many newtons this is, I could convert my 8 pounds to newtons if I wanted to, but there's and then I could measure the meters from here to my lever point, and the newtons times the meters would give me a newton meters of torque. Now, out here, if I hold it out here, from here to my lever point here, that's a lot more. So that's it takes a lot of torque. So yeah, obviously, I mean, you know this. Obviously, you know the right way to pick this up is from this end and not from that end. So it's just kind of funny to watch people do it. Another example of torque is like when you open a door here. Here we go. I didn't identify you on the video, did I? I didn't say your name. Good. You don't know who's weak. All right. So when I open this door from this side, I'm applying just a little bit of force. I can go and open it because I've got all this distance in between where I applied the force and the axis of rotation. So it just takes a little bit of force, but it's because I have all this distance. Torque is force times radius because this hinge, this makes a curved path when the door opens, and it's part of a circle. So that radius is the radius of this circle that this hinge would do if this door went all the way around. So yeah, just a little bit of force because I have a lot of distance, and torque is the force times this radius, and the radius is big, force is small. That's okay. If I come way in here and try to close the door, let's see. I can't do it. What if I use my thumb a little bit? Oh, I did it! Oh, ow. I have to make a really big force because I have a very small radius over here. So to make the same torque to make the effect I caused over here when I did this, I have to use a lot of force with a small, I have to use a large force with a small radius, because I only have to use a small force with a large radius. Force times distance is the same when I did the small force with a large radius as or force times radius, whatever, as the small radius with a large force. That's difficult. Anyway, I'm going to do one of these problems, the torque problems here. So, these pictures give the centimeters here and the grams here, and those aren't even what we like to use. We like to use meters, so 25 centimeters is 0.25 meters. 15 grams is 0.015 kilograms, and even that's not useful for torque, because this torque means that the torque, force times radius on this side, has to be equal to torque, force times radius on this side to make them balanced. And there's no mass in there, although we can split force up. Force is mass times acceleration, and that's what I did. I did mass times acceleration due to gravity to find the weight of each of these items. So this one is the 0.147 newtons, this one is the 0.078 newtons, and this one is the 0.033 newtons. And as you can see, there's a torque here, and the whole torque on this side has to be equal to this torque on this side, but there's two of them. And we can calculate the torque for each one, or we can separate them into two torques. So we've got this force and this radius, which we don't know. It's what we're going to solve for, that R. And this force times this radius out here. So let's do that. When I got my little paper right here. Come on. That's fine. When I multiply, well, let's plug everything in first. So force times radius over here is going to be, this weight is 0.147 newtons times that radius is 0.25 meters. And this one, that's the 0.078 newtons times, we don't know meters, that's the one we don't know. And then plus this other torque, oh, excuse me. That force is 0.033 newtons. Oh, I put the negatives there, good. Times, this one's 0.67 meters. And when I multiply all those, let's see, this times this is 0.0375. And that's newtons times meters, that's newton meters. That's another thing about torque. You guys hear people talk about cars, torque, and foot-pounds. That's just, the American way to do torque. When we do it in the science way, we use the International System of Units, SI units. And that's, instead of feet, we use meters. Instead of pounds, we use newtons. Pounds are our imperial unit of force. And that'll be fine. So yeah, they're the same thing, it's just different units. I don't know what that R is yet, so I'm just going to leave that. But let's see. This times this over here is 0.02278. That was a newton meters. All right. And I got a plus and negative here. I'm going to go ahead and change it to a minus. All right, so eventually, to solve for R, it says R times 0.078. I'll divide both sides by 0.078. But it says it's got this minus this over here right now. So I'm going to make that cancel first. Since it says subtracting this, I'll add 0.02278. I'll cancel because the negative that plus that makes the 0. I'll add it over here. Oh, dang, that's negative right here. I forgot. Plus 0.02278. The only reason I can add these is because they have the same unit. So when I do that, that plus that makes negative 0.015 newton meters. And that's still 0.078 newtons times R. And then when I divide both sides by 0.078, since this is our times 0.078. Okay. My answer, I get 0.19, that's the radius, so that's in meters. So apparently this one, if this were actually balanced, this one would be 19 centimeters away. This is one of the questions that's on your deal. It's not a required question. I did it because it's got these 2 torques on this side, so it's a little extra. I don't want to make y'all do it. Please try that out. If you need to finish your torque lab today, that's all right. I'm not counting those late yet.